Hi there, Jodie.
Hi, Jude.
Thanks so much for taking the time to speak to us today. It's really exciting that this is a great opportunity for any designers or engineers who are looking to basically create their own air quality sensing project, but have sometimes wondered a little bit about how do they choose the right sensor for the right application. So I'm hoping that together with a little bit of my design and engineering background and your data science background, we can give people a great overview here.
Hopefully.
So I should mention a little bit just that for people who aren't familiar with you, you're a DevOps engineer working at AirLogic Limited, which is a digital healthcare solutions company exploring data science of air quality and monitoring. You happen to have done a load of in-depth research in your PhD and thesis. But I thought it was also interesting just to be clear that you've also been incredibly helpful on the ESDK Air Quality Sensor Development Kit with DesignSpark in helping guide us a little bit on what is the best approach to take. Could you tell us a little bit just about how you got into sort of data science and air quality, and what is it that excites you about it in your current work?
Yeah, so my degree was maths and computer science, and sort of about halfway through that, there was definitely a focus on healthcare when it came to my projects and things, and that sort of slowly meandered into air quality for my master's thesis, and it just sort of blew my mind how interesting it was and how it affects everyone and how most people just don't consider it. It's just not something that sort of crosses people's mind. There was also direct calls from loads of different charities and organisations at the time that I was doing my thesis, asking for better air quality tools for end users and sort of sufferers of long-term like sort of lung-related illnesses.
Mm-hmm.
And so it was definitely sort of like there's a pressing need for this. And that was obviously a few years ago now when I graduated. And since then, that was in the middle of the pandemic. Since then, I think in my other interview, I touched on lightly that I plotted the pandemic. You could, on my graphs, you could see the sort of decrease in pollutants as we stopped sort of driving our cars around all the time when we went into lockdown. And since then, actually, I've been involved in a couple of different projects looking at indoor and outdoor, including the ESDK kits, which is phenomenally cool to be involved in, actually. Again, because I'm just a massive nerd about this stuff and really enjoy it. Oh, mine's in the other room. I should have brought it in. But yeah, it's like I say, it's something that affects all of us because we all breathe the air, and it's definitely a global problem. It's not something that just affects poor countries or rich countries or anything like that. It's something that it's looking at in general. And then again, sort of I moved from outdoor air quality when I was working on my thesis to now I focus a little bit more on indoor air quality, which is, I think, again, as I've touched on before, quite under researched and quite important because again, post pandemic, we spend a lot of time inside. Especially I
Absolutely.
think like if you do jobs like I do, like DevOps engineer, like I just sat in this room all day, 9 to 5. So it's really interesting. Yeah, there's lots that go into it.
And actually makes such a good point in that when I started out this work on the ESDK, really I was working with a sort of headline of how could we sort of do things to sort of help counteract pollution. And I definitely made, I wouldn't say the mistake, but I made the assumption in thinking it was all about cars, buses, trucks, factories, all this out external stuff. And you and me both know this WHO, World Health Organization statistic of, depending which report you pick, but let's just say a ballpark of around 8 million deaths per year is then approximately about 50-50 split on indoor and outdoor, which and I should probably stress for the audience, this is 2019 data, i.e. not muddied with COVID data. So I just found this absolutely extraordinary, and we quite literally did a 180 on the project, again with your help on saying, no, this really is this really is an underreported, under-researched area. Why is it that you think indoor air quality has, should we say, been dormant, is maybe the right word for it? It's definitely been
Yeah.
there, we just haven't seen it, the severity.
Yeah, so again, when I was looking for literature for my paper, we as a people have been looking at outdoor air quality for quite a while now. Like once we noticed pollution was bad, we started noticing how it has knock-on effects on us and stuff. And so studies into air quality started, sort of decades ago now. But again, there was just this massive focus on, oh, it's pollution, it's the industrial revolution, it's the cars, it's not, nothing in our home lives have changed. Whereas, actually things in our home lives have changed. Like I say, even just the fact that we're spending a lot more time at home now, a lot more people work from home now. Over the past couple of years, lots of people have been forced into their homes for elongated periods of time. But then also you've got things like the population and the housing crisis means that people are being stuffed into tiny apartments with not a lot of windows and not a lot of ventilation. And I've lived in rented properties where the cooker hasn't had an extractor and it's been a gas stove, and that's really bad. And again, I think the nuance of all that was lost on us for a while, because we just accepted that, oh no, we're fine. It's only really since the massive increase of like I say, sort of like cars and stuff like that, when we've started noticing, it having knock-on effects on us. But I think our homes are made of different things, our clothes are made of different things. People have different, like I say, windows, ventilation. Not a lot of homes sort of like, in the UK have like aircon or anything, or any type of ventilation, and so you rely on opening your windows to get the flow through. And I think people really started to realize how important that was around when COVID hit. So lots of schools, lots of universities, lots of hospitals were very, very interested in looking at sort of air turnover rates and flow rates and things like that, to make sure that, again, the buildings were being properly ventilated. Because, when a class changes over at 11 o'clock and you've got like 2,000 students walking in, 3 hallways, lots of windows in school buildings above the ground floor don't open. And so again, you've got because of health and safety, and that makes sense, and that's fine. But again, when you've got this sort of airborne disease and you're sort of thinking, okay, well, how can we reduce transmission rates? Is there something we can do with making the airflow better? And it's sort of like, oh, it starts to sort of, the penny starts to drop in there. Oh, well, actually, this airflow thing has a whole other bunch of knock-on effects on people's productivity and their ability to concentrate, but also health conditions.
Well, this is a great point, actually. As I don't know if you heard that little mechanical noise in the background, as that was actually my Air Quality Canary just going off, which has been made as part of this. Couldn't have timed that better, really. But the minute, because I'm closing the windows and the doors for the acoustic benefit of this interview, it's actually at just over 2,000 on CO2, which, for the sake of discussion, is actually a lot higher than it should be. Really, sort of humans shouldn't really exceed about 1,000. And so I think maybe one thing that's worth pointing out is that, as with so much in life, toxicity is also about the dose. So I'm suffering for the art for probably no longer than an hour. At worst, I might get a small headache. But obviously, if I was doing this every single day in an office, that would be a considerable effect.
Oh yeah, 100%. And there are loads and loads of sort of preliminary studies that help suggest that like CO2 and again sort of different air pollutants can affect our sort of the way that our brains work in different ways. Again, sort of like productivity.
So maybe we should just jump into that, because I'm aware that probably the designers and engineers out there are probably thinking, okay, tell me about the sensors. So maybe we should start off a little bit with the workhorse of the sensor world, which is the temperature and RH, which is this tiny little one here that has the cut around it. So I'll probably do a nice little close-up here in post-edit. But basically, these are minuscule little sensors. And I thought it was just worth pointing out that you might not think, if you're looking for pollution, do I need, humidity and temperature? But of course, how is
100%. 100%. The temperature and humidity is one of those things that affect everything in the air, right? Because it's just the way that it is. And it's really important, I think, especially when you're looking at seasonality and you're trying to look at trends. if you've got the humidity and the pollution, the humidity and the temperature and the pollution data to be able to stack against each other. You know, there's some very, very interesting, you know, I've seen very interesting findings when you're comparing that kind of data. Yeah.
So you mean you could have the same pollution in a very dry place or a very humid place, and what would that have a different, not just data reading, but would that actually have a different physiological impact on you?
Yeah, I mean, you know, sort of like, you know, when you go on holiday and the heat's different, or you climb a mountain and you're like, oh my gosh, I can breathe, it's so clean up here.
Yeah.
You know, sort of humidity can affect air quality in sort of that kind of way. You know, when the air's really humid and it feels really heavy, it can be, you know, it can have a little bit of a greater sort of toll on you. But also it affects the dispersion of the pollution as well, and so how quickly it'll clear or how long it will like hang around in the air.
How interesting. Yeah, this reminds me a lot of Hong Kong, where my partner's from. I remember hearing reports that they famously have all these, you know, wonderful signs all sticking out from the buildings as you go down the road. And actually there was mandate from the government to say, we have to take these down because it's restricting airflow through the city. And so it's not clearing smog. So
yeah,
I thought that was sort of just a really interesting example. I appreciate we're talking about indoor air quality, but sometimes you can't see the wood for the trees. So what would you say are some of the examples where, you know, looking at things like temperature and humidity indoors, how does that affect your life?
yeah, I mean, so there's also obviously optimal temperatures for us to be at and work
Right.
at, and you know, humidity as well. And so that obviously sort of plays a part. Again, if you're looking at sort of like how much sort of you can concentrate in a given sort of like composite minute, or you know, the sort of long-term effects. Temperature and humidity can be used sort of a bit like a proxy, I guess, as well inside, or it can help alert you before the air quality gets, you know, increases. I've seen on sort of some of my own personal graphs where the temperature and the humidity in the room gets a little bit higher, and then, you know, shortly after the pollution warnings start going off, and it's like, oh, so, you know, there's probably almost definitely a correlation there.
So in some ways, this is, I think this is so interesting for things like, I appreciate this was going to be a later question, but one of the interesting things about the Air Quality Canary is that, I should point out, this CO2 sensor cannot in any way detect COVID, but we're using it as a proxy to say if the air hasn't changed and the COVID level is a high, because that's associated with respiration, in other words, breathing out lots.
Yeah.
And not changing the air in the room, it's reason to say that that would be a statistical increase in probability of you transmitting and indeed catching COVID.
Yeah.
So what other things, it'd be lovely if you could talk about that a little bit, but are there any, I never knew the one about sort of temperature and humidity being a proxy for other things. If you could tell us any other little, I don't want to use the word hacks, but should we say rules of thumb?
Yeah. The temperature and humidity one's really good for, like, again, when I've been working with my ESDK sensor and just messing around with my sort of personal dashboards and things. There's definitely correlation there. I've possibly not studied enough data to give you anything sort of mega conclusive or bring up any graphs, but maybe next time. But I also think there's lots of interesting things about, you know, again, using it sort of as a proxy. If you're looking at indoor air quality and say we've got the sensors sort of like here, again, if the temperature is increasing and the humidity is, like, you know, sort of stable or increasing, it's possibly an indicator that I need to open the window, because it's getting too hot in here, which also means, you know, the air quality is accumulating, you know, there is no airflow if it's increasing. The other interesting thing for me, with temperature and humidity, is something else that's quite under researched, but it's about pollen, and so it's flipping a bit more back to outdoor, but there's not, you know, heaps of research. We
And there's
don't
still
really
pollen in
know.
your house. I mean, my wife suffers with hay fever. I can assure you, indoors is,
Yeah,
when
well,
you close the windows, is still a mystery to us, actually.
yeah, we've been suffering in this house terribly this year with hay fever. We've all been like constantly, where are the antihistamines? And that's, yeah, it is interesting because, you know, we can know that the pollen count's high outside and we can have the windows open, you know, for airflow.
Yeah.
But, you know, again, we don't necessarily know a lot about how different types of pollen move. And there's quite an interesting research space looking at sort of air quality and how air quality and pollutants distribute. And again, if there's research into whether we can use that as proxies for pollen, or if we can look at sort of, you know, dispersion patterns and then see if we can find a way to sense different types of pollen and maybe use like that model. And so that's really cool. I also think, I know I said earlier that air quality doesn't discriminate necessarily between like rich and poor countries, and that like everywhere has their own different problems to deal with. But I think again, in warmer countries, you do typically see that they have, like on the world maps and stuff, you do see that the air quality tends to be a bit poorer. And so again, there's definitely space for research there.
And I think that's one of the things where, you know, I'm not going to name any names, but sometimes when you phone up the absolute elite in a specialist world, there can sometimes be a little bit of perfect or nothing. And I think that's one of the things where, I mean, pollen is literally staggeringly small. And certainly, I mean, it's sort of, am I right in the sort of 0.3 micron level? It's this famously irritating size, which our body can neither purge nor completely absorb and then urinate or excrete out. And so it creates havoc with our bodies. And yet I kind of feel that when you look at the notion of saying, is your challenge to detect the difference between horse chestnut pollen, rapeseed oil pollen, and grass pollen, for a sensor that is as tiny as the one I've just shown you, basically a little bit bigger than a sort of pinhead, it's crazy to think that that sensor could possibly do that for a price that you want. And yet, if you're saying that you could create products which are accurate even 80% of the time, that would be a game changer for people's windows. I mean, I know that no plugs intended, but Velux already has a automatic IoT window that you could close. The notion that your house could say, I don't know if there's pollen out there, but the humidity's done the thing, and now I'm going to execute the rule, close all the windows, and put on the air purifier inside the house. That feels believable, right?
Yeah, 100%. I mean, like me and my partner, he's techie too, and we've discussed at length, you know, building our own sense network in for the house that controls like all kinds of stuff. You know, switches on air purifiers or switches on the heating in the winter. Like, it's because for me that would be ideal. Like, I would love to know that the air that I'm breathing isn't necessarily putting me at risk. Again, even at just a lapse of concentration, let alone sort of like anything prolonged or triggering anything that's sort of dormant. But the sort of the IoT space that's connected to air quality as well, especially in the home and like in the offices and schools and stuff like that. Again, phenomenally expansive. So much room to sort of explore.
Well, strangely, one of my other hobbies at school actually was ceramics, and I remember being warned considerably the importance of wiping down wet, not sweeping, because the silica that would go in the air was hugely carcinogenic and is a classic cause of death of anyone who's worked in ceramics in the days pre, you know, adequate PP ventilation and indeed just awareness. But I thought maybe that's a good segue into this little plugin, which people might recognize with its cover on, looking like that. But nonetheless, this is a particulate sensor from Sensirion that we were using, and it basically sorts particles into, should we say, buckets of PM1, 2.5, 4, and 10. To the uninitiated, it'd be great if you could tell people a little bit what's happening. And again, I might put a little cutaway in post at this moment of basically explaining that the air would travel along this side here across that little sensor, whereby a laser is shot at it, it scatters into that shiny sensor and is then pulled out by this fan.
Yeah.
Could you explain a little bit, like, what are some of the design considerations? Because as with all sensors that are, should we say, non-million-pound laboratory grade, you got to be aware of a little bit of you're getting what you pay for, right?
Yeah, 100%. I think there's, again, I know that we've discussed this, but you know, for all the other people interested, there's a massive element of sort of common sense involved in this kind of stuff. If the sensors are, you know, claiming to be phenomenally accurate and they're phenomenally cheap, then I'd probably sort of steer away from them. But there's definitely sort of set your expectations to what you're paying for. The reason why our sensors are like this big and not, you know, huge, massive industrial ones is because the huge, massive industrial ones that the government use are mega expensive and they're not practical. And so
And you
we've
certainly
got
can't carry them around. So,
no, you know, I couldn't move that from my office to the bedroom to the kitchen just on a whim. It'd be a nightmare. So I think, you know, yeah, it's common sense to sort of say, right, it's affordable, it's small, but that doesn't necessarily mean that it's not useful, right? So anything where you're comfortable with the accuracy being roughly right, anything that you can use that indicate trends and stuff like that, you know, you might be slightly over or slightly under, but if you've got, you know, consistent, if your data is consistent with your data, then you've got data to make comparisons from, right? So again, as I know we've discussed, there's a big network called Purple Air, which is very, very similar to the DesignSpark sort of sensor network. Actually, they sort of started by marketing reasonably priced sensors, and you can just buy one, put it wherever you want, hook it up to their system, and it sends them the data, and it gives you your data. And they're sort of notoriously, or they were sort of notoriously known for not being the most accurate. And I think, only have a particulate matter sensor as well, to be honest. But then somebody did a group of people did a paper that was sort of supported by the American government. And they essentially worked out an algorithm to course correct their data and just make it a little bit more accurate. So after, you know, collecting enough data, they were able to compare to the big fancy sensors that the government use and sort of say, okay, well, yeah, we're slightly over in this, or we're slightly under in this. And then they applied that algorithm to the rest of the data. And so it, you know, increases the accuracy, it normalizes it. And so there's always opportunity for things like that. But, you know, also a sensor that's, you know, 70-80% accurate, like I say, if your data is consistent with itself, then you definitely obviously still got something to compare against. And there's, you know, plenty of online resources to help you sort of figure out what sensors are capable of, or how you can use those sensors and compare it with other data sets.
So, and maybe that's a good point to say that, for example, again, this isn't sponsored by or anything like this. This was genuinely just in the research that we were doing. This is the Flow 2 sensor from Plume Labs, and this is basically an NO2 gas detector. So basically, these will both claim NO2 detection. The sensor in this is probably in the order of, you know, a very small amount, and it measures particulate and all sorts of other things. Whereas this is, you know, a 200-pound plus industry grade one for sort of basically having people walking around, you know, test facilities or places of risk. I mean, it's very rugged, and they do all sorts of things for methane and things like this for miners. So the accuracy implied in these two things is very different. This is about saving your life and being correct. This is about citizen science and being
raising awareness.
Exactly. And I just to be clear, if anyone from Plume Labs is watching, this isn't dragging or sort of belittling them at all. This is simply just saying what they excel at isn't lab grade accuracy. What they excel at is creating really nice UI UX design, great maps, great ways you can look and share data. And of course, you could say somewhat the ESDK that we've been building sort of arguably falls somewhere in the middle. It probably needs to improve its UI UX a little bit, but at the same time, it's definitely not having to, you know, lug around 6 of these basically.
Yeah, so again, it's sort of, you can even get, you know, you can get sort of indoor air quality sensors even from IKEA now. I think I looked, and they're like 10 or 12 pound, and again, it's just particulate matter, and they have a little light on there, you know, that's just sort of green or red. And so, you know, of course, like you say, those kind of sensors are nothing like you know, sort of lab grade sensors, because they're designed for different use. And so I think as long as you, as the developer or sort of like project runner or whatever you sort of call yourself, as long as you're aware of that, that's what's important. Like I say, it does sort of come back to common sense. And I think if you're interested in this kind of stuff, like I say, there's loads of research and sort of resources online that can give you a lot more information. Even just sort of like the spec guides for each of the boards can you know, provide you with.
Maybe one of the analogies that I thought you sort of, you know, when we got into early discussions, this for me sort of reminded me of something which I had sort of studied back in my uni days, of how these blood pressure monitorers, you know, from a purist perspective, these are not as accurate as anything that you'd get in a hospital, because those machines cost literally thousands of pounds. This is sort of like, you know, 20 quid or whatever. And I think what I found sort of really helpful in relating to this project as well was that, you know, these two words in engineering come up a lot, of accuracy versus precision. So, you know, as they say, a clock can be, you know, right even twice a day, right? A stop clock. And so this isn't in any way a highly accurate device. Let's say the error is like 10%, but the relative error of this from one reading to the next, the precision in that is completely reasonable. So if I monitor myself for a month and the trend is creeping up or creeping down or stabilizing, a doctor would say, well, really, I'm interested in you reporting the trend to me. Should it get dramatically worse, I'm going to ignore your particular numbers, but I'm very interested in the fact that things have got worse, so let's come in for a checkup. How would you, well, obviously I've made the point very clear that the relationship between that and air quality sensors, but just to take a sort of bigger holistic view for people wanting to explore air quality projects, what would you say are some of the most exciting trends for people to dig into, in your opinion?
I mean, I really enjoyed the COVID trends on my personal graphs. That was just mind blowing at the time. Like logging on after a couple of months and being like, wow, that's a very, very, very clear drop off. But I think in terms of our kits specifically, and again, sort of like focusing back on indoor air quality, I've been really, really interested in looking at the air quality, like I say, sort of in the office throughout the day, and wondering and trying to sort of notice if certain pollutants are high, if I'm particularly less motivated, or, you know, sort of struggling to concentrate. And again, there are a couple of the studies out there that sort of that dig into that in a little bit, not just me. You know, they have some sample sizes, some varying sample sizes. And so there's that. There's also sort of like, I'm really interested in air quality in the kitchen. Again, I've got a gas hob, and that just kicks out so much crap. I think Pete did his Grafana talk, didn't he, about cooking the bacon sandwich. And so if people are interested in sort of air quality in the kitchen, I would recommend checking that out. But there's, you know, also what I mentioned to you, that our textiles, our fabrics, our soft furnishings in our homes, they can hold stuff. You know that your sofa can hold smells, but they can hold pollutants as well, right? But so can your curtains, and so can your carpets, and so can your desk mats. And I'm not saying that they're, I guess,
your mattress as well. Your mattress, where you spend almost a third of your life, right?
Yeah. So I'm not saying these are all, you know, holding terribly dangerous amounts of pollutants, but it's definitely something that we don't know. Like, we just don't know. And so that that's really, really interesting for me. Again, sort of what I've touched on, airflow through buildings as well. That I also find really, really interesting. Again, some of our windows in this house don't even open. And so again, it's like, well, how can we maximize the airflow? How can we utilize the windows that do open to make sure
Yeah.
that, you know, upstairs is cool and it's clean. And yeah, you can sort of apply that to hospitals, schools, universities, massive offices.
So I think what you've described is such a great response to saying, you know, how do you sort of create good proxies, good triggers to say this is not industry leading science, but it's a heads up that something is deteriorating and needs a closer look. I thought maybe that would be a good opportunity to jump into the difference between a discrete sensor and a general sensor. And maybe an example of, you know, just to give a little bit of a what's in the pipeline for DesignSpark, we're looking at a dedicated formaldehyde sensor. Now that is chasing one molecule very, very accurately. It's a little bit expensive, but it doesn't really want to do anything else. It just wants to do that. And then similarly, I think this is maybe the one most people are familiar with, this tiny little speck of a thing, which is beside the temperature sensor here. That is the MOX sensor, or metal oxide sensor, sometimes called a VOC sensor, but actually now has the capability of both oxidizing and reducing gas analysis. So this is the moment when I'll pop up Sensirion's little primer. And I was wondering, could you just sort of talk through a little bit? What are some of the considerations when not getting too confused with thinking you're detecting everything when really you're detecting a general reading?
Yeah, again, this comes back to, I think, looking at your board specs and again, understanding what you've got in whatever sensor you own. I think, again, the cheaper your sensor, probably as a general rule, the more general your sensor is. It's probably got sort of reduced capabilities in that sense. But again, so with like VOC and stuff, they are not, you know, necessarily focusing on one very specific thing, but again, they can act as a proxy and as a general sort of warning, I guess, as opposed to actually tracking individual pollutants, which is useful if you're trying to focus on an individual pollutant. Like if you are very, very interested in NO2 or CO2 in the air, then like that's fine. Go and spend some money on getting a very, very good dedicated board for that. But I guess I think it goes back to dependent on what you're trying to monitor as well and what you're interested in. But for most people, I think like the more general, there's a middle ground. I think like you want a little bit of general, but you know, still good enough that you're confident that you're
absolutely, and
you know what you're picking up.
I'm sort of reticent that we might scare people off with the sort of chemistry things, but I feel sometimes when you look at the data sheet from Sensirion and it says, well, reducing gases will have this response and oxidizing gases, I think it's really actually quite reassuring how good the internet is that you just type in, is methanol a reducing or oxidizing gas, and it'll tell you, you know. And so then you have an understanding of really how is that going to create a reading on the MOX broadband sensor. But I think what's rather interesting about all of this, and I think it's something you've touched on, but I just wanted to re-stress it for viewers, is the notion that if you could walk into a lab that does have fancy gear, and you said, well, let's compare the fancy gear readings to the, you know, the budget ones, let's see if they fall within, you know, appropriate bands, that you could say, well, we know even if it's 20% error on my tiny little $5 sensor, 20% error is fine. Because I need to detect, you know, kind of yes, no, the problem is big or the problem is small type of accuracy, not plus or minus 0.1%.
Yeah, I think this is another thing that if you have an interest in air quality, you've probably seen already, or even if you've just been on the weather iPhone app since the last update. Air quality is normally done in bands. So it's normally like good or okay
like
or
smiley
bad.
face, happy face, sad face, isn't it? It's
Yeah,
that level.
or yeah, like traffic lights
Yeah.
or whatever sort of, you know, lots of, you know, different companies, different governments do it slightly differently, but it all sort of, you know, it all does come back to this sort of like banding level. And so again, when it comes to like mega accuracy, that's only really, really important if you are doing like, you know, a paper, and very, very specifically concentrating on one thing, or you know, you need to do something to a certain level of sort of precision and accuracy. But yeah, in general, like I say, if your data is consistent with itself, it's just like the sort of the blood pressure thing. You have something valuable to compare it against then.
So that's terrific. I think maybe a good question to sort of finish on is, you know, we've talked a lot about in some of the recent materials about this thing which we're calling activist engineering, which, you know, internally we've sort of referred to it as, it's great if engineers can take to the streets and protest, but actually engineers are uniquely placed to take to their, let's say, workshops or sheds or laboratories, but actually build solutions or provocations that might move the needle on some of these issues. So I was wondering, what are your sort of hopes and aspiration for where, you know, the convergence between industry, governments, and citizen science converge?
Yeah, I'm hoping that people, I don't know how many people it would need, but enough people, enough engineers, enough scientists, enough people that are interested in data and air and conservation and global warming and all that stuff, just sort of like we can all come together and we'll all look at a tiny little different area and a little bit, because we're all interested in loads of different stuff. And then eventually we'll be able to sort of take a big step back and look at everything, you know, that we discover over the next couple of years, whether that's finally being able to track pollen, understanding how air quality, you know, works, and, you know, having a better understanding of how sort of like modern fabrics and materials and stuff can absorb and hold on to different pollutants, just like anything and everything that we've discussed in this call, and even more. And hopefully at some point that will form this like big picture of how our current air quality is, and hopefully will guide us into this is what we need to do to make it better.
Well, that's terrific. That's a tremendously inspiring note to finish on. So thank you so much, Jodie. As I said, I've absolutely loved working on this, and it's been great to see all the other sort of projects around it, from the 50 people that have been gifted environmental sensor development kits to the so that is almost as if by cue. I didn't plan this, but I'm now at just over 3,000 parts per million. So this is surely a good time to wrap up the interview.
Yeah, we need to end this call so you can open your windows.
Thank you so much, Jodie. It's been a real pleasure, and I do hope people also check out the DesignSpark blogs, all the other air quality influencers, and of course some great other interviews and content from yourself. So thank you again.
Yeah, cool. Thanks for having me, as always.
Take care. Thanks a lot, Jodie.
Bye.